Ask anyone to name a concept from quantum physics, and they will likely point to Schrödinger's cat. It's become the unofficial face of the atomic realm, a hypothetical animal trapped inside a box, existing simultaneously dead and alive. The standard takeaway is that reality is subjective. Many believe the experiment shows that the cat remains in this suspended dual state until a human observer opens the box, forcing the universe to choose a definitive outcome. But Erwin Schrödinger did not invent this scenario to explain quantum mechanics. He invented it to demonstrate how absurd the theory had become. In 1935, Schrödinger described the experiment as a quite ridiculous case. It was a calculated, sarcastic critique designed to embarrass his colleagues for accepting a mathematical model that ignored objective reality. Schrödinger was targeting the measurement problem, the inability of the reigning equations to explain exactly how a blurry subatomic probability becomes a single physical fact. The cat serves as a record of a bitter, unresolved intellectual war between the founding fathers of modern physics. In the mid-1920s, quantum mechanics was developed by a tight-knit network of physicists working across Göttingen, Copenhagen, and Munich. From this circle emerged Niels Bohr's Copenhagen interpretation. Bohr argued that subatomic objects exist in all possible states simultaneously until they are observed. He famously described the subatomic realm as an Alice in Wonderland sort of place. By October 1927, leading physicists gathered at the Fifth Solvay Conference. The collective authority backed Bohr's unintuitive vision. Leaders like Born and Heisenberg officially declared the theory closed, insisting the mathematical assumptions were no longer susceptible to modification. For rebels like Einstein and Schrödinger, this consensus felt like a fantasy that ignored the existence of a real, definitive world. 8 years after the Solvay summit, Schrödinger launched a counterattack. He designed a logical escalator meant to drag subatomic weirdness up into the visible world. His setup involves a diabolical steel chamber. Inside, a radioactive atom connects to a Geiger counter, wired to a relay releasing a hammer poised above poison. The system is triggered by a 50-50 chance the atom decays within an hour. If the atom decays, the counter triggers the hammer, creating a mechanical chain reaction. The state of the macroscopic device is now tethered to the microscopic atom. The hammer drops, the flask breaks, and the cat is poisoned. Schrödinger pointed out that, according to Bohr's logic, the unobserved cat must be considered both dead and alive simultaneously, mixed or smeared out in equal parts. He compared the situation to a shaky photograph. A blurry picture of a clear landscape doesn't mean the landscape itself is blurry. It means the camera is out of focus. The absurdity of a half-dead cat proved that the Copenhagen interpretation was incomplete. It failed to define where the quantum world ends and our world begins. Niels Bohr largely ignored the paradox. He simply declared that macroscopic objects like cats were too big to have wave functions, though he never specified exactly how big an object had to be for the rules to change. This left a glitch in the foundation of physics. The core mathematics of quantum mechanics has no mechanism to explain the collapse of the wave function into a single reality. In 1957, Hugh Everett proposed a solution. Wave functions never actually collapse. In the many worlds theory, the moment the box is opened, the universe divides. Every possible outcome exists as an actual reality in a different branch of the multiverse. Everett turned Schrödinger's sarcasm into a literal mathematical map of reality. Pop culture quantum physics often treats observation like a magical human power. The reality is far more grounded. We are still grappling with the quantum classical divide. We still don't know exactly how the quantum blur solidifies into the definitive world we inhabit. The cat on the t-shirt marks the boundary of our knowledge. It is a reminder of the unsolved transition between the math of probability and the physical world we touch.